Hi, this is lesson 18 for linear algebra, section 4.2. Today we learn about null spaces and column spaces of a matrix and how they relate to matrix transformations. We're also going to learn about row space. Okay, so there's a little chart that helps us with some of the terminology from the section. The null space of a matrix lives in the domain of a linear transformation. T of x equals a times x. And the null space is the set of all things that get mapped to the zero vector. And then the range of the linear transformation is the column space of A. Okay, some examples. Consider the matrix A is 1, 4, 2, 5 in the null space of A. So the definition of null space is the set of all things that A times it equals 0. So I want to solve A times x equals the 0 vector. So all of these x's that make this equation true are part of the null space. So to test a particular vector, I'm going to multiply the matrix A times the matrix X and check and see if I get the 0 vector. So this is a 2 by 4, this is a 4 by 1. I can multiply them because the inner dimensions match, and my result should be a 2 by 1, 2 rows, 1 column. Okay, so we multiply these, the first row times the column vector, and we get 0 minus 4 plus 4 plus 0. And then the second row times the vector gives me 1 plus 4 plus 0 minus 5. Do that arithmetic out and you get 0, 0. Okay, so A times x does equal 0, so yes, x is in the null space of A. 1, 4, 2, 5 being in the column space is 1, 4, 2, 5 in the column space of A. The column space of a matrix is the set of all linear combinations of the columns of A. So if you look at the columns of A, linear combinations of them means put a weight on each one and then add them all together. Which means my result would have to be a vector with 2 entries. So this is impossible because col A must live in R2. The only way you can take a linear combination of the columns of A is to put weights on the columns of A and add them together, and that's going to give you a vector with 2 entries. So there's no way 1, 4, 2, 5 could be a linear combination of the columns of A. All right, is 1, 4, 2, 5 in the row space of A? Why or why not? Okay, so the row space of A is the set of all linear combinations of the rows of A. So that means we're going to treat each row in A as a vector. And if we put a weight on it, if we put weight, are there weights that we can put on those 2 vectors to get 1, 4, 2, 5? So let's see, my vectors, I'm going to write them vertically because that's what we're used to. I'm writing the rows of A vertically because that's how we're used to visualizing vectors. Okay, so this question is saying, are there weights that I can put on those 2 vectors to build 1, 4, 2, 5? So I could set up an augmented matrix and row reduce. So this row reduces to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, Okay, so we want to translate this to equations, and this says A equals 0. B equals 0. 0 equals 1, and 0 equals 0. So this right here tells me that this has no solution. This is inconsistent, which means there's no solution, which means there are no weights A and B that can make this equation true. So it is not in the row space. That vector is not in the row space. Okay, same matrix A is 3, 7 in the null space. So that is asking, is A times that matrix times that vector equal to the 0 vector? So we'll test it. 0, 1, negative 1, 1, 2, 0, 0, negative 1 times 3, 7. Does that equal the 0 vector? So the matrix A is 2 by 4, and this vector 3, 7 is 2 by 1, and these inner dimensions don't match. You can't even multiply them together, let alone get the 0 vector. So this is definitely a no. And the reason is that elements of null A must live in R4. You'd have to have 4 entries to even be able to multiply A by a vector. You would have to have 4 entries. Is 3, 7 in call A? So that is, are there weights that I can put on the columns of A? So A times 0, 1 plus B times negative 1, 1, C times 2, 0, D times 0, negative 1. Are there weights that you can put on the columns of A to build 3, 7? That's what it means to be in the column space, because the column space is the set of all linear combinations of the columns of A. So to solve this, you make an augmented matrix and row reduce. And you get 1, 0, 0, 1, 2, negative 2, negative 1, 0, 10, negative 3. Okay, so this is consistent. There is no line that says 0 equals a number. There's actually infinitely many solutions. So the answer is yes. We can find weights that can build 3, 7 from the columns of A. And I'm not actually asking to find the weights, so all I need to say is yes, because I know that there are some. Is 3, 7 in the row space of A? So that's saying if you treat the rows of A as vectors, so 0, negative 1, 2, 0, and 1, 1, 0, negative 1. Treat the rows of A as vectors. Are there weights that you can put on them to build 3, 7? And the answer is definitely not. The answer is no, because the row space, any element in the row space would have to have 4 entries. Elements of row A must live in R4. You take a linear combination of 4 entry vectors, you would get a 4 entry vector. Okay, number 2. Consider the following row equivalent matrices. Find an explicit description of null A by giving a set of vectors that span the null space of A. Okay, so to find the null space of a matrix, that means find all the vectors such that A times the vectors we're looking for, x, give you the 0 vector. Okay, so I have already done the row reducing. Imagine that I augment, to solve this equation, you would just augment A with zeros and row reduce, right? And I know that what you get would be this with zeros attached to it. Okay, so my null space would be the solution set here. So I'm going to write this down as equations. This says x1 plus 2x2 equals 0. x3 plus x7 equals 0. x4 plus 4x5 plus 2x6 equals 0. And the last row tells me nothing. So my pivots are x1, x3, and x4. So I'm going to solve for those. x1 is negative 2x2. x3 is negative x7. And x4 is negative 4x5 minus 2x6. I'm going to put that in parametric vector form, the solution set. x1, x2, x3, x4, x5, x6 equals, I need a vector associated with each free variable. So my free variables are x2, x5, x6, and x7. Then I just fill in these vectors to match these three equations. So x1 is negative 2x2. So in the first spot in the x2 vector, I'm going to put a negative 2. And then zeros everywhere else. And then x2 is one of my free variables, so I just need x2 equals x2. So I'll put a 1 there and zeros everywhere else. x3 is negative x7, so I want a negative 1 in the x7 vector, zeros in the other 3. x4 is negative 4 x5, so I'll put a negative 4 here, minus 2x6 and put zeros in the other 2. And then x5 is free and x6 is free. So I need a 1 here for x5, zeros everywhere else. And x6 equals x6, so I'm going to put a 1 there and zeros everywhere else. So that's parametric vector form. So this is a description of the null space. This is the null space of A. But they asked me to describe it as the span, a set of vectors that span the null space. So I just have to remember that span means the set of all linear combinations of a set of vectors. So what I've written here is all the linear combinations of these four vectors, because x2, x5, x6, and x7 are all free, which means they can be any value you want. So this is, I could rewrite this as the span of these four vectors. Okay, so that is the description of the null space they asked for. We described null A by giving a set of vectors that span the null space of A. I can pick any weights I want, x2, x5, x6, and x7, except for all zeros. They just can't all be 0. because that would give me the 0 vector, which I'm not allowed to use. So let's make them all, I don't know, 1. Make them all 1. I'm going to copy this to the next page. So I'm going to copy A. Okay, give a non-zero vector in null A. Okay, so I'm just going to jump back here. Okay, so if I make all those weights 1s, I would get -2 plus 0 plus 0 plus 0, 1 plus 0 plus 0 plus 0, 0 plus 0 plus 0 plus -1. I'm going to run out of space here. Okay, and then fourth entry, I've got 0 minus 4 minus 2 plus 0, so -6. And fifth entry, 0 plus 1 plus 0 plus 0. And the sixth entry, I would have a 1. So that's an element of the null space. Pick any values you want for the weights. I did 1s. Okay, find an explicit description of call A by giving a set of vectors that span the column space of A. Okay, the definition of call A is the set of all linear combinations of the columns of A, which means that the column, if you take the span of the columns of A, that's call A, right? So call A is all linear combinations of the columns of A, which is the span of the columns of A. So all I have to do is list the columns of A here, and I have a spanning set for call A. I'm just going to leave it like that. Any non-zero vector in call A, I could add them all together. I could just pick any weights you want and put them on the columns of A. So let's okay, so there's A. A non-zero vector in call A will be any linear combination of the columns of A. So you just put some weights on each of the columns. Maybe I'll do like 2 times 1, 1, 0, 3, -3, plus -4 times 2, 0, 6, -6. And then I'll put zeros on everything else. So this comes out to 2 plus -8 is -6. 0. 6 plus -24 is -18. And -6 plus 24 is 18. Okay, find an explicit description of row A by giving a set of vectors that span the row space of A. So the row space, remember, is the set of all linear combinations of the rows of A. So I have 4 rows here in A. They each have 7 entries. So row A is all linear combinations of the rows of A, which means that is the span of the rows of A. So all you have to do is list the rows of A and you have a spanning set. Very similar to finding a spanning set for call A. Give a non-zero vector in row A. Any row of A would do. Or any linear combination of the rows of A. Pick any weights you want and put them on the rows of A. I'm going to write them vertically because that's just how I'm used to looking at vectors. And let's see, this first row, I'm going to give a weight of 2. And the second row and third row, I'm going to give a weight of 0. And then the fourth row, I'm going to give a weight of 1. So I'm going to get 2 plus -3 is -1. 4 minus 6 is -2. 0 plus 3. -2 plus 2. -8 plus 8. -4 plus 4. And 0 plus 3. A non-zero vector in row A.